My name is Doug Edwards, and I'm a PC, and I'm using Apple products this morning, so I'm going to be doing a little bit of dancing back and forth with the mouse. Again, the name is Doug Edwards. I'm employed by Energy Solutions. I've been a nuclear industry for, I'll put it this way, since 1980. My first 11 years were supporting commercial nuclear power plants, primarily writing procedure programs, developing training programs, and training reactor operators, as well as health physics technicians. In 1991, we moved to Aiken, South Carolina, and began supporting the Department's energy side of the house, and have been here ever since. This presentation, if I were to go through it slide by slide, it would take just 2 hours. What I recommend is, when you receive your CD, I don't know if you have your CD already for presentations, please feel free to add to it, take away from it, as you see fit to suit your purposes. It's impossible for me to put together a presentation that meets the needs of all people, so I didn't attempt that. The first part of the presentation, I recommend that you home in on original nuclear theories. Focus on people. When you, in the PowerPoint presentation, you'll see learning objectives that are stated. They're repeated at the end. There's a little summary included in it. I'm not going to go through all those slides this morning. I am going to stop on this slide and detour myself just a little bit. My oldest son and my only daughter are teaching fellows. And 6 years ago, I had an opportunity, 7 years ago, I had an opportunity to attend a teaching fellow event. And one of the speakers was the president of the University of South Carolina upstate. It used to be Spartanburg. And he made a comment that has stuck with me. And this slide is up here for my benefit. Thought I would share it with you. He described 3 kinds of teachers. The first kind of teacher is an average teacher who gets the job done. What makes that teacher an average teacher is the teacher discusses and explains information. And then he talked about a second category of teacher, the good teacher. The good teacher is the one who not only explains and describes, but demonstrates. But the third type of teacher, and I have a feeling I'm surrounded by them, nearly, is the exemplary teacher. And that's the person who inspires students to pursue, to yearn for knowledge, to learn information on their own. And those are the students who are going to step forward and take these basic fundamentals, advance them even further. The nuclear industry started a long time ago. Early Greek philosophers, to the best of my knowledge, they're the first to introduce the concept that all matter is built of some sort of a building block. The early Greek philosophers, they thought the 4 basic elements were earth, air, water, fire. It's a good thing those philosophers didn't live in the 1970s, because we might have confused them with Earth, Wind, and Fire, the rhythm and blues popular music band. By the way, in the notes section, there are links throughout the presentation where, if you want to use this information, you're welcome to. From 450 BC, Democritus, he talked about indivisible particles that made up things. And that theory just sat on a shelf until the 1600s. Then Boyle came along and came up with the concept of elements and realized, you know, there's more than 4, and maybe those 4 aren't exactly correct. 200 years later, Dalton comes along. Says elements are actually made up of atoms, and atoms are unique. So there's a big gap between 450 BC and the 1800s. One of the questions that your students may ask about atoms is, how large is an atom? A quick activity. My wife wouldn't let me bring scissors this morning. The way the activity works is, and this is something you can do in the classroom, take a sheet of paper. If you trust your students, give them scissors. If not, say, take a sheet of paper and cut it in half. 1, Take 1/2, cut it in half. 2, 3, 4, 5. Oops, that was a bad 5. 6, 7, 8, 9, 10. After you get to 12, do that 90 more times. And I brought one with me just in case you wanted to see it. You'll get down to an atom that's about this big. So, size of an atom. Not until the late 1800s did we start progressing with more theories. Beautiful story. I encourage you to go online, research it, check out books in the library about the Wilhelm Röntgen, his wife's hand, and Henry Becquerel. Earliest X-ray that I'm aware, discovered quite by accident. Becquerel had a box, as the story goes. A drawer is what it was described. It had a photographic plate in it, and he had a sample of uranium that he'd been experimenting with, and he put them all in the drawer. Then Röntgen's wife, quite accidentally, left her hand. They opened the contents of the drawer. The photo plate was exposed, and there was an X-ray. So that got people thinking. The Curies, Marie and Pierre, I could spend easily 90 minutes talking to you about them. But as far as atomic fundamentals are concerned, the two things to get across from their discoveries: some elements emit energy, others emit particles. So we started with Greek philosophers talking about indivisible particles. That evolves. People started attacking the theory, started proving, started modifying, started revising. So where I'm going with this particular narration is this material is not only good for nuclear science, chemistry, electricity, but it gets into the scientific approach as well. J.J. Thomson, I think that stands for John James? Can't remember. John James took this information from 2,000 years earlier, started building on it, and came up with the first published theory that was accepted about what an atom looks like. And he came up with what was called the plum pudding model, where the pudding portion was positively charged goo, and the plums were what we now call electrons. So a group of guys got together to examine this particular theory. Ernst Rutherford was the leader, Geiger, Marsden, those were his assistants. They set out to prove the theory. And the way they decided to prove the theory was to take a piece of gold foil. They have an emitter that's called an alpha emitter, two charged, positively charged particles. What they wanted to do was to target that piece of foil, surround it with zinc sulfide, because when alpha particles hit zinc sulfide, it produces a flash. So what they were expecting to happen, I told you I'm a PC. What they expected to happen was for the alpha particles to pass through the plum pudding. But that's not what happened, which is going to lead us to our first activity. What happened instead, they got flashes all the way around, which meant that the alpha particle didn't go straight through or immediately get kicked back. Let's do this experiment. Come follow me in an orderly fashion. We have tables, we have chairs, we have a piece of wood.
We have it set where there are 5 stations, so I think if you break up into teams of 4 or 5, it'd be, you can go to a station.
After you take a seat, please go ahead and open the marbles. I'll help this table. What our marbles represent are alpha particles. Now, this piece of wood, don't look, don't look, don't look.
not look under the board.
Do not look under the board. What this, did you see? What this piece of wood represents is an atom.
You need one thing to write with as well. Just one.
We have alpha particles. We have atoms. On the underside of the atom is the nucleus, or the center of the atom. So if this experiment went the way Thomson predicted, what should have happened is the alpha particle, if you put it on the table, flip the marble, should simply go straight through. Experience for yourselves what happened. It didn't. There is a test. Underneath, the nucleus of your atoms is a geometric shape. Your mission, like Rutherford, is to determine what that geometric shape is. So what we're going to do, and we have a piece of paper so you can draw the shape, anything to help. Each of you take marbles and just roll them through, see what happens. And based on whether the marble goes through or if the marble ricochets, guess the shape. And I think we have a door prize for whoever draws the shape to scale. Okay, what you're going to do is roll it underneath. You may need a little bit more spin on it. Huh. You guys are on top of it. Good catch, Carol.
Each one that goes through,
yeah. Based on the way it ricochets, come up with a geometric shape.
So I guess this would be the shape.
Oh.
So it's like that, right? Let me see if I can go to that.
What Rutherford was able to derive from his activity is the alpha particles were bouncing off something positively charged. It was being repelled and being sent off in different directions. They decided that it was a proton because it was positively charged. The alpha particles were positively charged. That would be the repulsion. Later, they decided that the center of an atom is called the nucleus. The nucleus of an atom has almost all the mass of an atom, and from their experimentation, they were able to determine, because of the large number of alpha particles or marbles that pass straight through, the bulk of an atom is nothing more than empty space, which makes us phantoms of sorts, doesn't it? How much of an atom is empty space? Atoms. Remember, I had one in my pocket. I misplaced it. I'm not sure where it went. By the way, I read a very interesting quote. Probability is very high that during your lifetime, you will have breathed the same atom, at least one of the same atoms, that Albert Einstein breathed, that Aristotle breathed, and that Earth, Wind, and Fire breathed, along with all the people at their concert. Diameter, very, very, very small, to the -10th meters. I mean, we're talking extremely small. But to get this in perspective, you've got a hydrogen atom. Let's pretend if a hydrogen atom had a 6-foot diameter, how far away would the nearest electron be? What we can derive, and the notes are in your presentation, is that the nearest electron is over 50,000 diameters away. So your 6-foot hydrogen atom nucleus, 568.2 miles away. A lot of empty space. Hence the comment about phantoms. We did this activity. More atomic theory. the theories in the early 1900s just took off. And it's amazing. I mean, I'm amazed in my lifetime all of the technology that is advanced. When I grew up, television did exist, contrary to what my children believe, but it was all black and white. And then color television came out. Now we've got 3D television. Same thing with the story of atoms. This technology took off. When mail comes up, you're going to be very surprised at all of the things that rely on nuclear science to work. Everything to the quantity of cola that comes in the can or the bottle that you enjoy during lunch or a break. Getting back to Rutherford studies, Bohr came up with the first model of an atom that was accepted after Thomson's model. Bohr was correct in that the nucleus or the center of an atom had positively charged protons, and that surrounding or swarming around the atom is negatively charged electrons. If you have sharp students, someone's going to figure out, well, if the nucleus is positive and these electrons are negative, shouldn't they attract? What keeps the atoms from colliding? What keeps the electrons from colliding into the positive nucleus of the atom? And that's an excellent question. My explanation, I like to keep things simple because that's the way my mind works. Atoms are constantly in motion. For that electron to hit the nucleus of the atom, that would be like driving your automobile, rolling down the window, and trying to take a baseball or a tennis ball and strike a billboard with it while you're driving 55 miles an hour. They're rotating very, very fast. I've mentioned already, atom consists of negatively charged electrons. Each electron, I just had a technical glitch. Electrons have their own quantized amount of energy. This slide and the notes that go with it talk about how electron energy is quantized. We're going to talk about that. It talks about how it's gained and how it's lost in bundles. I've got an illustration to show that a little bit later if I'm operating this correctly. What happened with the Bohr model was we realized something had to be holding those positive protons together. Otherwise, they would want to repel and break apart. And what they figured out is that there are neutrons that act as a glue within an atom. This model is what we use in commercial nuclear power. It's all right to call this model the Bohr model. You got positively charged protons, neutral neutrons, and swarming around the atom, negatively charged electrons. And lots of space. A term that you want to get your students to learn is anytime you talk about a nucleon, you're talking about the center of the atom. The nucleus. A nucleon can be either a neutron or it can be a proton. Subatomic particles, they're very small. They have distinct locations, they carry charges, and they have a mass. Atomic mass units, something that you want to brush up on before you begin teaching the material because it's very, very light, very, very small. But the bulk of the mass of an atom, based on these numbers, if we round this up to 1, this up to 1, and this, whoops, that worked. Okay. It heard me say I am a PC. Page up, I think. This is a nice little chart that you're welcome to use if you're creative with PowerPoint. What you may want to do during your presentation is to set it up where the name of the particle appears first, along with the top row information. Then as you talk about each one, advance it, and this information should fill in. Nucleus, neutron, proton, swarming around. And I use the term swarming. I was at Augusta State University a couple of years ago, and I was rather surprised with the way that they are illustrating atoms now. What they're doing is taking a piece of chalk, drawing with the chalk the neutrons and the protons, and then taking the chalk, turning it sideways, and just making it a cloud. I have trouble visualizing that. I like the old Bohr model a little bit better because it's easier for me to comprehend. Periodic table of the elements. Elements are a single atom or groups of atoms that are identical. When we talk about elements, when we talk about atoms, normally if I say hydrogen, zinc, something like that, we're really referring to the periodic chart. Now, if I start talking about zinc 65, zinc 66, zinc 67, which is the atomic mass, that's where the term nuclide comes into play. A nuclide is nothing more than an atom where you're being more specific about that particular atom. This is known as the AZ nomenclature for an atom. A is the atomic number. The atomic number is the number of protons that the atom has. For an activity that Bill is going to take you through later, you need to remember that protons define what the atom is. At the bottom on many charts, it's the atomic mass. If the mass of an electron is negligible, pretty much what you're seeing right here is the total number of neutrons and protons. Round it up, round it down. Just follow normal rounding rules. Let's do a quick math problem and get ahead on the slides. Zinc, we round it. It's going to be 65 for a total mass. If it has 30 protons, oh, I did?
It's okay. You still have to.
Oh, can you tell me? Can you tell me how many neutrons are in that atom? Come on, somebody tell me. Thank you. Like I said, this particular presentation can be used to introduce chemistry. It can be introduced as well as electrical science. This might be a good slide that you want to use. What this is showing is the orbits of the electrons that go around the atom. Orbit number 1, 2, 3, we call those shells. The maximum number of electrons that can be in that orbit. 2 in the first, 8 in the next, 18 in the next, 32. There's actually a formula for where you can calculate how many electrons can go around that atom. The outer shell of an atom is called the valence shell. What this is showing is happy atoms. That's what I like to call them. If the valence shell is filled to the max for an atom, it's happy. It's not very aggressive. It's not looking for other atoms to swipe electrons away from or to share. Helium, argon, neon. On the periodic chart, all of those are on the left-hand side. They line up really nice and neat. Unfilled valences. This is where you get into your more aggressive atoms, atoms that are wanting those outer shells to be filled. Lithium, sodium, potassium. There's different kinds of reactions. You've got chemical reactions. In this one, you've got 3 unhappy atoms. Their outer shells aren't filled, so they come up with a solution. You've got oxygen roaming out here, wanting 2 more electrons. You've got 2 hydrogens floating around. They want another electron so that they can be happy. So what they wind up doing is sharing. Yes?
And this is why I tell the kids that water likes to hug.
Water likes to hug. I like that.
It sticks. No matter what it is, it sticks to you. You can't stick your hand in a bowl full of water without it sticking.
Yeah. Now what I tell my kids is if you take this one and flip them upside down, you got Mickey Mouse. Excellent point. Thank you. Nuclear reaction's a little bit different. We might have a neutron flying along, runs into a nuclide, lithium-6. The lithium-6 absorbs the neutron, becomes lithium-7, and then it splits. I've got to stop. There we go. What happens is 2 new atoms are now formed. We've got a helium atom and a hydrogen atom. And the math always works out. Ionization, a term that you want your students to nail down. An ion is an atom that has either gained or lost electrons. Ions can be positive, ions can be negative. We should have a couple of slides. If you look at it, you have a balanced atom. It loses an electron. Let's say something collides with it, absorbs the energy, and the electron decides to leave. You now got a positive atom. The reverse is also true. Chemical formation of ions. Do you recognize sodium and chloride? Common table salt. Nuclear formation of ions. This was what I tried to describe a few minutes ago, where radiation strikes the electron absorbs the energy, it becomes excited, and it exits the atom. And now we're left with an ion. Nuclides. Nuclides are simply atoms. When we talk about nuclides, instead of saying atoms, if we say nuclides, we're talking about specific combinations. Mass number, in this notation, is always on top. Atomic number, what's your atomic number? Number of protons, that defines what your atom is. The chart of the nuclides, this is a commercial for Bill's presentation that's coming up later. You're going to get very familiar with it. But do remember the number of protons, so that you're selecting the correct nuclide, defines what the atom is. Enough for commercials. There's an example of a stable nuclide. Bill's going to talk about unstable nuclides as well. Isotope. Those are unique combinations of protons and neutrons in an atom. In hydrogen, who can tell me what's normally in hydrogen as far as the nucleus is concerned? Jump in, jump in. Okay, that isotope we call protium. Deuterium, tritium. You've got a proton, 1 neutron. Normally there's not a neutron. So isotopes. To my knowledge, these are the only 3 isotopes that get names. Everything else is referred to with numbers. Ah, you could have read it. They're the same isotopes of hydrogen. Forces on the nucleus. 3 kinds of forces: gravitational, electrostatic, and strong nuclear. Gravitational, the attraction of masses that they have towards one another. On the atomic scale, that interaction is very weak. Attractive forces between the nucleons, very long-lasting. Electrostatic force, that's where you get the repulsive, your positives and your negatives. Good little chart that you may want to use in your presentations. And that brings us to our final activity, and I'm somehow way ahead of schedule.
That's all right. Gives more time for others.
When we talk about energy and wavelengths, AM/FM radio has a very long wavelength. Microwave, there's more to it. You can see the scale when you get up to X-rays. Let's go ahead and do the activity. Let's do the activity. I need 4 volunteers.
2.
What do you? This will be a chance to work out.
You pick out the volunteers and I'll help them line up.
Okay, who volunteered? Come on up, come on up, come on up. What this activity is going to illustrate is a relationship between the energy and wavelengths. Again, there's other areas of science. Light and sound. Okay. Let's take our first group. What I would like you to do, and this is going to require, again, teamwork. Strongly recommend that one of you do the moving and the other just hold it. let's produce an FM radio frequency. It's a very long wave.
Yeah. When I have introduced waves to my kids, obviously, guys, I'm a lot younger than you are. There's all different kinds of waves, hello waves, goodbye waves. And from my wave, we understand that the wavelength for radio is as long as a football field, from trench to trench. Is that right?
Variable. That's right. Okay, but we're going to make a long wavelength wave, so it's long on the scale, relatively.
I think that's pretty long. We also brought some jump ropes. I'm not sure which is going to work better, a shorter distance. I think the longer distance is going to work better when you do this particular exercise. Okay, next group. What kind of energy are we going to produce here? You want to go for the?
You can hold.
Let's go with that ultraviolet. Let's do the ultraviolet. Yeah.
No.
There we go. You've nailed it.
Ultraviolet. It was going round and round, but it works for me.
Okay. Now, energy relationships. Which one of those two required the most energy?
Ultraviolet.
Ultraviolet. Both groups. Let's make X-rays.
It must be kind of tight and little. Come on, Kate.
Well, let's experiment. Let's see what happens when you get closer and go fast, and then what happens when you get further apart. This works for health and phys ed as well. Ooh.
And then tight.
Well, you know, round works good for me.
Or on the floor.
No, if you're on the floor, then you can go this way.
Another method that I've seen this done is to take a slinky, and what you have to do is take one end and attach the slinky to a table or an object that's going to hold it. That's actually much easier to deal with. It's also real easy to tangle the, at least I have a knack for tangling the
Stretch
slinkies.
it out
Right.
and put it together, yeah.
Yes.
Also the ruler, the wooden ruler on the edge of the table. And if you move it further away and you bling it, it makes a different wavelength than when you move it in and bling it.
I've done that, but I've never associated it. Did everyone hear that? Taking a ruler or a yardstick.
You put it on the edge of the table and you flick it.
That's good time.
And then,
Well, we talk about sound waves and
Yeah.
light waves, and so an illustration is a wooden ruler. See, it's nice, and then you shorten it, and they see, and you hold it actually right here. And then and you can also feel it, so the table can't. Versus, and then still hold it here. But it's a different kind of way.
Thank you very much. And that actually wraps up my presentation. Hopefully these are activities that you can use. Talked about the Bohr atom, electrons, they swarm on the outside. We talked about elements where you have identical atoms in a chemistry discussion. You want to talk about molecules where you have different families of atoms working together to form compounds, mixtures, substances. The basic subatomic particles. Bottom line is I hope you're able to use this information in the classroom.
did you say that was on the CD?
Yes.
Do we have it? 'Cause I couldn't-
You will get it. We
Okay.
have more.
We'll get it.
At lunch, we're gonna get sleeves for them, they're on sleeves.
Oh, okay.
So we
Yeah,
can-
got to buy sleeves, but we got CD for each
Uh-uh.
person that has
It's
all
in
of these
PowerPoint,
presentations.
I think it's, depending on who made it, whether it's in the new or the old. So.
I think they're all 2007, and then there's an additional folder with a bunch of supplemental information, just interesting information about that John Pullman mostly put together on nuclear facts.
Yes.
Just had a quick question about the isotope notation. Why is it called AZ? I'm just curious.
I don't know any stories about it.
Okay.
John, do you have a story?
What is it?
Why is isotope notation is called an AZ format?
I don't know how they picked that.
Okay, just something a high schooler would
Yeah,
ask.
they
And
do
we're
that.
required to teach them
Things.
two ways. You know, the AZ format that you show, as well as the name of the or element or the symbol, the element, the dash, and then the
Right.
mass number.
Yeah, there are two ways, but there is a standard, common notation is that AZ is the standard, but we
They
see
have
it
to
both
know.
ways.
They have to know both. I mean, the AZ, of course, I always tell them is the easier of the two because all your information is there. The other way, you have to, you know,
Do some math.
you got to do math. You got to go to the periodic table and find the atomic number.
We're gonna do some exercise on it in, not the next lecture, but the one after, so we'll talk about it again, so.